Somewhere in the silent black beyond our solar system, a small spacecraft built in the 1970s is still moving. Right now, as you hear this, Voyager 2 is drifting through interstellar space at over 34,000 miles per hour, and it has been running from the sun for nearly 50 years without stopping. But here is what almost nobody realizes. If you could somehow follow Voyager 2 forward in time, not 10 years, not 1,000, but 1 full million years into the future, something strange happens. The spacecraft would still exist. It would still be moving. And yet, when you look at where it ends up on a galactic map, the result is so unexpected, so humbling, so quietly terrifying, that it forces you to rethink everything you assumed about distance, speed, and what it truly means to leave home. Before we go any further, if you enjoy these slow, deep explorations of space, a quick like or subscribe really does help this little channel keep going. No pressure at all, just a small tap that means more than you know. Now, let's begin. Right now, as you sit wherever you are, as you breathe, as your heart quietly beats, there is a small machine made of metal and wire and old 1970s engineering drifting through the blackness of space at a speed you cannot really comprehend. It is not orbiting anything. It is not slowing down. It is not being pulled back. It is simply leaving, as it has been leaving for nearly 50 years, moving outward from the sun in a direction that takes it farther from Earth with every single second that passes. And it has no intention of ever stopping. That machine is Voyager 2. And to understand where it will be 1 million years from now, you first have to understand what it is doing right now, at this very moment, in real physical space. Voyager 2 was launched on August 20th, 1977. That date alone should give you pause. When this spacecraft left the surface of the Earth, riding on top of a Titan IIIe rocket from Cape Canaveral in Florida, the personal computer was barely a consumer idea. The internet as you know it did not exist. Most of the people who would eventually grow up to study Voyager 2's data had not yet been born. And yet, that small probe, weighing about 720 kilograms at launch, roughly the weight of a small car, was already designed to outlive every single engineer who built it. It was not meant to do what it is doing now. That is one of the most extraordinary things about it. Voyager 2 was designed as a planetary probe. Its original mission was to study the outer planets of our solar system, to fly past Jupiter and Saturn and send back data about those strange, distant worlds that had only ever been seen through telescopes. That was the plan. A few years of work, some good pictures, some good science, and then silence. That was what the engineers at the Jet Propulsion Laboratory expected. But the planets lined up. And when the planets line up, something becomes possible that almost never happens. A configuration called a grand tour, where a single spacecraft can use the gravity of one planet to slingshot itself toward the next, saving enormous amounts of fuel and time. This alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, occurs only about once every 175 years. Voyager 2 launched at exactly the right moment to take advantage of it. And so, instead of just visiting Jupiter and Saturn, it went on. Over the next 12 years, it flew past Jupiter, then Saturn, then Uranus, and finally Neptune, completing the most ambitious planetary tour ever attempted, by a single spacecraft. To really understand what Voyager 2 accomplished before beginning its interstellar drift, you have to appreciate what it actually did at the outer planets. The science it returned during those 12 years of planetary encounters rewrote our understanding of the outer solar system. When Voyager 2 arrived at Jupiter, it returned images of the gas giant that added enormously to what its sister craft, Voyager 1, had already revealed just months earlier on its own faster flyby route. Voyager 1 had discovered Jupiter's thin, dusty ring system and the active volcanoes on its moon, Io, the first active volcanism ever seen on any world other than Earth. Voyager 2 followed up on those discoveries, observing the volcanoes continuing to erupt on Io, and returning the most detailed images yet taken of Europa, Jupiter's strange ice-covered moon. Europa showed a cracked, fractured surface, crisscrossed with long dark lines, hinting at the possibility of a liquid water ocean hidden beneath the ice. Ganymede, the largest moon in the solar system, revealed a complex surface with ancient cratered regions and younger grooved terrain. The Great Red Spot was still raging, and every moon was a surprise. At Saturn, Voyager 2 arrived about 2 years later. Once again, it built upon discoveries Voyager 1 had made the year before. The rings of Saturn, which from Earth-based telescopes had looked like simple broad bands, were revealed to be composed of thousands upon thousands of narrow ringlets, structured in patterns of astonishing complexity. Voyager 2 refined those observations, captured better images of several small shepherd moons that keep the rings in place through their gravity, and studied the strange hexagonal pattern in Saturn's northern clouds, a six-sided atmospheric feature that still puzzles scientists today. It also measured the thick orange atmosphere of Titan from a distance, extending what had been learned about that moon. At Uranus, a few years later, Voyager 2 made perhaps its strangest discovery. The planet was lying on its side, tilted almost 98 degrees from its orbital plane, so its rotational axis pointed nearly directly at the Sun. No other planet did this. The cause, astronomers now believe, was a catastrophic impact billions of years ago that literally knocked Uranus over. Voyager 2 was the first and only spacecraft ever to visit Uranus, so every single discovery there belongs entirely to this one mission. It found 10 previously unknown moons orbiting Uranus, bringing the known total at the time to 15. It discovered 2 new rings around the planet, and it imaged the bizarre fractured surface of Miranda, a small moon that looked as if it had been shattered into pieces and reassembled by some unknown cosmic event. The images of Miranda remain some of the strangest pictures ever returned from the solar system, and they exist only because Voyager 2 went there. At Neptune, the most distant encounter of its entire planetary tour, Voyager 2 arrived 12 years after launch. There it discovered the Great Dark Spot, an enormous storm similar to Jupiter's Great Red Spot, along with winds of over 1,500 miles per hour, the fastest winds ever measured on any planet. It imaged Triton, Neptune's largest moon, and found geysers of nitrogen erupting from its frozen surface. Triton remains one of the coldest places ever measured in the solar system, at about minus 391 degrees Fahrenheit. That it had active geysers despite being so unimaginably cold was one of the greatest surprises of the entire mission. All of this science, every photograph, every measurement, every discovery was made possible by a clever piece of orbital mechanics called a gravity assist. This is worth understanding because it is what made the Grand Tour possible in the first place. When a spacecraft approaches a massive planet on a carefully chosen trajectory, the planet's gravity pulls the spacecraft toward it, accelerating it. If the geometry is right, the spacecraft does not get captured by the planet. Instead, it swings around and is flung outward at a higher speed than it had before, stealing a tiny amount of the planet's orbital momentum. The planet slows down by an almost imperceptible amount, and the spacecraft speeds up dramatically. This is how Voyager 2 was able to reach Neptune at all. Without the gravity assist from Jupiter, Saturn, and Uranus, the spacecraft would never have had enough energy to make it that far. Each planet kicked it farther along, boosting its speed and bending its path to align with the next target. Voyager 2 is still the only spacecraft in human history to have visited all 4 of the outer giant planets. No other mission has done it. No other mission is planned to do it. Because of how rare the planetary alignment is, no other mission will be able to do it for more than a century. The scientists who designed the trajectory knew they were taking advantage of a celestial window that would not open again for generations. And they made sure Voyager 2 used every moment of that window to its fullest. That alone would have justified the entire program. But when Voyager 2 finished with Neptune, it did not stop. It could not stop. It was moving too fast and there was nothing left to slow it down, so it just kept going. That is where we find Voyager 2 today. Still going. Still moving. Still sending back the faintest whisper of a radio signal to receivers on Earth that strain to hear it across a gulf of distance that is almost impossible to describe. Let us try to describe it anyway. As of the current moment, Voyager 2 is approximately 13 billion miles from Earth. Write that number out. 13 billion, not 13 million, which would already be staggering. Not 1,300,000, which is roughly the distance to the moon several times over. 13 billion miles. To give you some sense of that, if you could somehow drive a car from Earth to Voyager 2 at a steady highway speed of 60 miles per hour, without stopping, without sleeping, without refueling, it would take you about 24,700 years to reach it. 24,700 years of continuous driving. That is longer than the entire span of recorded human history. That is longer than the time since the last ice age peaked. And Voyager 2 would not even be waiting for you. By the time you arrived, it would be much, much farther away. In the units astronomers prefer to use for distances inside the solar system, Voyager 2 is currently about 139 astronomical units from the Sun. An astronomical unit is the average distance from the Earth to the Sun, roughly 93 million miles. So Voyager 2 is more than 139 times as far from the Sun as our planet is. For comparison, Pluto averages about 39 astronomical units from the Sun. Voyager 2 is more than 3.5 times farther out than Pluto. It is far beyond every planet, every dwarf planet, every well-known object in our planetary neighborhood. Light itself, that impossibly fast cosmic messenger, takes time to cross this distance. A radio signal sent from Voyager 2, traveling at the speed of light, takes about 19 hours to reach Earth. Think about that for a moment. The light you see from the sun is only about 8 minutes and 20 seconds old when it hits your eyes. The light from the moon is only about 1 1/3 seconds old. But the signal from Voyager 2 is 19 hours old by the time it reaches us. If Voyager 2 had a problem right now, the engineers on Earth would not know about it for 19 hours. And if they sent back a command to fix it, that command would take another 19 hours to get there. The system that allows us to communicate with Voyager 2 at all is itself a remarkable engineering achievement that deserves its own moment of appreciation. It is called the Deep Space Network, and it consists of 3 enormous radio antenna complexes, spaced roughly evenly around the planet. One is in Goldstone, California, in the Mojave Desert. One is in Madrid, Spain, and one is in Canberra, Australia. Together, these 3 sites provide continuous coverage of the sky, so that no matter how the Earth rotates, there's always at least one dish pointing in the right direction to hear from Voyager 2. As the Earth turns and one station loses line of sight with the spacecraft, another station picks up the signal without interruption. It is a global infrastructure dedicated almost entirely to the delicate work of listening to things very, very far away. The dishes themselves are huge. The largest at each side is 70 meters across, which is nearly 230 feet in diameter. They are precision instruments, built to track distant objects with incredible accuracy and to filter out the tiny signals of spacecraft from the overwhelming noise of the universe. And the signals they're trying to catch are, by any reasonable measure, absurdly faint. By the time Voyager 2's 22-watt transmission reaches Earth, the signal strength has fallen to levels measured in attawatts, which is 1/billionth of a billionth of a watt. It is, as mission engineers have pointed out, less power than a single snowflake hitting the ground would release as kinetic energy. And yet, we hear it. That faint signal, after 19 hours of travel, still carries information we can decode. The Deep Space Network also handles communications with every other active deep space mission, from Mars rovers to probes at Jupiter and Saturn. Voyager 2 has to share time with these other missions. As the spacecraft gets farther away and its signal grows weaker, it requires more and more of the network's resources to hear it. There is a real, practical limit to how long we can keep listening, not just because of the spacecraft's failing power, but because of the diminishing returns of dedicating our most sensitive antennas to an ever fainter whisper from an ever more distant machine. Every conversation with Voyager 2 is a 38-hour round trip. That is not a conversation. That is archaeology with a time delay. And yet, even at that distance, Voyager 2 is still talking to us. Its transmitter, powered by decaying plutonium, emits a signal of about 22 watts. 22 watts. That is less power than the small light bulb inside your refrigerator. That tiny whispering signal crosses 13 billion miles of empty space and is caught by enormous radio dish antennas on Earth. Dishes that are part of a system called the Deep Space Network. These dishes are dozens of meters across, and they have to listen very, very carefully to hear Voyager 2 at all. The signal arriving at Earth is so weak by the time it gets here that it's often described as being trillions of times fainter than the signal from a digital watch. And yet, we still hear it. We still receive data from it. It is one of the most extraordinary ongoing feats of engineering in human history. Now, the question you might be asking is, how fast is Voyager 2 actually moving? Because speed is what determines everything about this story. Speed is what put it where it is. Speed is what will carry it where it is going. Speed is the central physical fact of Voyager 2's existence. Voyager 2 is currently traveling at approximately 34,391 miles per hour relative to the Sun. In metric terms, that is about 15.5 kilometers per second. Let me put that in a form you might actually feel. A commercial jet airliner cruises at about 500 to 600 miles per hour. Voyager 2 is moving more than 57 times faster than that. A rifle bullet leaves the barrel at around 2,000 miles per hour. Voyager 2 is moving more than 17 times faster than a bullet. The International Space Station, which orbits the Earth at breathtaking speed, moves at about 17,500 miles per hour. Voyager 2 is moving about twice as fast as the space station. And yet, in the context of the distances we are about to talk about, this speed is almost pitifully slow. That is one of the great lessons of this whole story. By human standards, Voyager 2 is moving incredibly fast. By cosmic standards, it is barely moving at all. It is adrift. It is a creep. It is the steady, patient crawl of something that has all the time in the universe and is in no particular hurry to get anywhere. The direction Voyager 2 is heading is also worth thinking about for a moment, because it is different from where Voyager 1 is going. Voyager 1, its sibling spacecraft, was launched about 2 weeks after Voyager 2, but because it took a more direct route, it actually arrived at Jupiter and Saturn first. After Saturn, Voyager 1 was flung up and out of the plane of the solar system, heading generally toward the northern sky. Voyager 2, by contrast, took the longer road, visiting all 4 outer planets, and was eventually flung downward and southward out of the solar system. So while Voyager 1 is heading roughly in the direction of the constellation Ophiuchus, Voyager 2 is heading toward the southern sky, in a direction that takes it through the constellation Telescopium, near the celestial south. Neither spacecraft is aimed at any particular star. That is important to understand. When people first hear about Voyager 2, they sometimes imagine it was pointed at some distant destination, that it is flying towards some specific place, that it will one day arrive somewhere meaningful. That is not how it works. Voyager 2 is not aimed at anything. Its trajectory is simply the result of its launch, its planetary flybys, and the gravity of the Sun. The direction it is moving in is whatever direction it happened to be moving when it left Neptune behind in 1989. It is a spacecraft on an escape trajectory from the solar system, and space is what it has, and space is what it will cross for the rest of its functional existence and for millions of years beyond that. The spacecraft itself is a marvel of old engineering. Voyager 2 carries instruments that were state-of-the-art in the 1970s and are now, by any modern standard, primitive. Its onboard computer has less processing power than a modern pocket calculator. Its memory is measured in kilobytes. Its tape recorder, yes, tape recorder, was the primary way it stored data for decades. And yet, these systems, designed before most of us were born, have been functioning continuously in one of the harshest environments imaginable: the vacuum of space. the cold of the outer solar system, where temperatures drop to hundreds of degrees below zero. The constant bath of cosmic radiation. Voyager 2 has been exposed to all of this for nearly 50 years, without a single visit, without a single repair, without a single human hand reaching out to fix anything. Everything it does by itself. Its power source is a set of 3 radioisotope thermoelectric generators, often called RTGs. These devices do not use solar panels because of the distances Voyager 2 is traveling. Sunlight is far too weak to power anything useful. Instead, they generate electricity from the heat of decaying plutonium-238. When Voyager 2 launched, these generators produced about 470 watts of electricity. Today, they produce less than half that, because the plutonium has been steadily decaying for nearly 5 decades. Every year, the spacecraft gets a little weaker. Every year, the engineers at JPL have to make difficult decisions about which instruments to turn off in order to keep the essential systems running. Voyager 2 is, in a very real sense, slowly going dark. Within the next few years, it is expected that all scientific instruments will have to be shut off. And at some point in the 2030s, even the transmitter will go silent. The conversation with Earth will end. But here is the extraordinary thing. Even when the conversation ends, Voyager 2 itself will not end. It will not slow down. It will not stop. It will not fall back toward the sun. It will not die in any physical sense. It will simply go dark. And it will continue moving at roughly the same speed, in roughly the same direction, for a length of time that is effectively forever by human standards. There is almost nothing in the vacuum of interstellar space to slow it down. No air to create drag. No significant gravity from nearby stars for an extremely long time. The spacecraft that Voyager 2 is today is essentially the spacecraft. It will be 1 million years from now, physically speaking. A cold, silent piece of human technology, still moving, still crossing space, still out there somewhere. This is the hardest thing to wrap your mind around, and it is the foundation of everything we are going to explore. Voyager 2, right now, this very moment, is in the act of becoming a permanent part of the galaxy. It is no longer just a mission. It is no longer just a probe. It is quietly, steadily transforming into something closer to a geological object, a piece of debris that will exist for timescales that have nothing to do with human lifetimes or human civilizations. We built it. We launched it. We communicated with it for decades, and then gradually we will lose it. Not because it goes anywhere dramatic, but because it simply keeps going forever, in a way we cannot follow. To really feel this, consider what Voyager 2 has already done in 48 years of flight. It has traveled about 13 billion miles. At its current speed of 34,391 miles per hour, it covers roughly 300 million miles every year. Every single year, it moves about 3.5 astronomical units farther from the sun. It is not a dramatic motion. You would not notice it if you watched. But it never ever stops. And each year that it keeps going, it puts another 3.5 astronomical units between itself and home. There is something beautiful about this, and also something deeply lonely. Voyager 2 is, in many ways, the most isolated object we have ever created. The astronauts who walked on the moon were only about 250,000 miles from home. The deepest submarines in Earth's oceans are only a few miles below the surface. Even our most distant Mars rovers are at most a few 100 million miles away. But Voyager 2 is 13 billion miles out. It is farther from us than anything else we have ever built, with the single exception of its sibling Voyager 1, which is currently even farther, at about 15.5 billion miles. These two probes, Voyager 1 and Voyager 2, are the most distant human objects in existence. Nothing else is even close, and they are both, at this very moment, in the process of crossing a boundary that nobody on Earth can see, that nobody can touch, but that is as real as any border you have ever crossed. Voyager 2 already crossed this boundary in 2018, and that crossing, that moment when a human object passed from one kind of space into another, is where everything really starts to open up. But before we get there, I want you to sit for a moment with where Voyager 2 is right now. Close your eyes if you like. Think about the direction of the constellation Parvo in the southern sky. Now imagine a point out there, 13 billion miles away, far beyond anything you can see, far beyond Pluto, far beyond the outermost edges of everything humanity has ever mapped as a planet. That point is not empty. There is something there. Something small and silent and cold. Something with the gold-plated record of humanity attached to its side. The golden record, with recordings of music and greetings in dozens of languages and images of Earth, and diagrams of our DNA. Something that was once on this planet, assembled by human hands, and is now there in the void, moving at 34,000 miles per hour, carrying a tiny piece of us through a universe that did not ask for it. That object is Voyager 2, and it is still going. Every second that passes, it moves about 9.5 miles farther away from you. In the time it takes you to draw a single breath, Voyager 2 covers more distance than most people walk in a day. In the time it takes you to watch a full-length movie, Voyager 2 travels 68,000 miles, more than 2.5 times the circumference of the Earth. In the time it takes you to sleep a full night, it travels more than 250,000 miles, roughly the distance from here to the moon. These are not abstractions. These are happening right now, as you exist. And when the Deep Space Network finally stops receiving its signal, sometime in the 2030s, when the last watts of plutonium-powered electricity fade and the transmitter falls silent, Voyager 2 will not fall. It will not drift into a star. It will not be caught by anything. It will just continue. Silent, dark, cold, moving at 34,000 miles per hour through the empty spaces between the stars. And it will do this for a length of time that makes all of human history look like a blink. This is the spacecraft that we are following. This is the machine whose future we are trying to trace. And before we can answer the question of where it will be in 1 million years, we have to understand what it means that this object, right now, this very moment, is no longer really part of the solar system at all. Because Voyager 2 has already crossed one of the most profound boundaries in our cosmic neighborhood. In November of 2018, something happened to it that only one other human object had ever experienced. It crossed the edge of the sun's influence. It entered interstellar space, and that crossing, that moment, is what turns this from a story about a spacecraft into a story about what it truly means to leave home. On November 5th, 2018, something happened that almost nobody on Earth noticed. There were no headlines screaming the news on most front pages. There was no sudden cultural moment, no global pause, no worldwide celebration. And yet, on that day, for only the second time in the history of our species, a human-built object crossed a boundary so profound, so invisible, and so strange that it fundamentally changed what that object was. Voyager 2 left the sun's protective bubble, it crossed the heliopause, and in doing so, it stopped being a spacecraft operating within the solar system, and became something that had never really existed before in our language. It became an interstellar object, a tiny metal, plutonium-powered piece of humanity now drifting in the space between stars. But what does that actually mean? What is this invisible border, and why does crossing it matter? And here is the part that most people find genuinely surprising. Even though Voyager 2 has left the sun's bubble, it has not really left the solar system at all. Not in the way you probably think. The solar system, in its fullest and truest sense, extends far, far beyond where Voyager 2 is today. And the story of how we define the edge of our home, how we draw the line between here and out there, is stranger and more beautiful than most people realize. Let me start with something you probably already know, at least a little bit. Our sun is a star. It produces an enormous amount of energy through nuclear fusion in its core. And that energy radiates outward in every direction. But the sun does not just give off light and heat. It also gives off a continuous stream of charged particles, mostly protons and electrons, flowing out from its surface at speeds of hundreds of miles per second. This flow is called the solar wind. And the solar wind does something remarkable. It carves out a bubble in the surrounding interstellar gas. This bubble is called the heliosphere, and it is, in a very real sense, the sun's territory. Inside the heliosphere, the solar wind dominates. Outside, it does not. Outside, a completely different kind of medium takes over. The interstellar medium, made up of the thin, cold gas and dust that fills the space between the stars of our galaxy. The edge of the heliosphere, the boundary where the solar wind finally loses its battle with the interstellar medium, is called the heliopause. And that is the boundary that Voyager 2 crossed in November of 2018. When it crossed, the instruments on board, instruments designed and built in the 1970s, suddenly registered a change. The density of charged particles jumped. The magnetic field shifted. The spacecraft had physically moved from one kind of space into another. It was a measurable, detectable, scientifically verifiable event. For the first time in its life, Voyager 2 was no longer bathed in the sun's wind. It was feeling, for the very first time, the thin, cold gas of the galaxy itself. To understand how extraordinary that is, consider what Voyager 2 had been swimming through for more than 40 years. From the moment it launched, every particle it encountered, every magnetic field line, every bit of plasma that brushed against its metal surface came from the sun. It was surrounded by our star's influence. Even at Pluto's distance, even at twice Pluto's distance, even at 100 times Earth's distance from the sun, it was still inside the solar wind, still inside the heliosphere, still inside, in a meaningful physical sense, our sun's territory. And then, one day, it crossed over, and the wind that had been at its back for 41 years was simply gone. This boundary is not a hard wall. It is not a sharp line. The heliopause is more like a shifting, fluttering membrane that pushes and pulls as the sun's activity rises and falls over its 11-year cycle. But for Voyager 2, the crossing was relatively clean. One day it was inside, the next it was outside. The transition was detected by its plasma science instrument, which, remarkably, had been turned off on Voyager 1 years before due to a malfunction. So Voyager 2 was able to give us a kind of data that no other spacecraft had ever provided. A direct, working measurement of the boundary itself. And the measurements that Voyager 2 sent back were full of surprises. Scientists had expected the crossing to show a clear change in the direction of the magnetic field. The reasoning was simple. Inside the heliosphere, the magnetic field comes from the sun, carried outward by the solar wind. Outside, the magnetic field should come from the galaxy itself, a completely separate source with its own orientation. The two fields should point in noticeably different directions, but when Voyager 2 crossed, the field direction barely changed. The magnetic field on the inside and the magnetic field on the outside were, unexpectedly, almost perfectly aligned. Nobody had predicted this. It suggested that the sun's magnetic field somehow shapes or imprints itself on the nearby interstellar medium, creating a smooth transition rather than a sharp discontinuity. This discovery forced scientists to rethink basic assumptions about how our heliosphere interacts with the galaxy around it. There was also the question of cosmic rays. These are high-energy particles, mostly protons, that race through the galaxy at close to the speed of light. They come from distant supernovae and other violent cosmic events, and they have been traveling for millions of years by the time they reach our part of space. Inside the heliosphere, the solar wind acts as a partial shield against these galactic cosmic rays, deflecting many of them before they can reach the inner solar system. So, scientists expected that when Voyager 2 crossed the heliopause, it would suddenly detect a surge in cosmic rays as if the shield had been removed. And that is exactly what happened. The instant Voyager 2 crossed over, its instruments registered a sharp increase in the intensity of high-energy particles, confirming beyond any doubt that the spacecraft had left the sun's protective bubble. There was also the question of the so-called bow shock, the theoretical region where the heliosphere plows into the interstellar medium at supersonic speeds, creating a shockwave like the wake of a ship. For decades, scientists had assumed this bow shock existed, but data from Voyager 2 and other missions suggests that the heliosphere may be moving too slowly relative to the surrounding medium for a true bow shock to form. Instead, there may be only a gentler bow wave, a region of compressed gas without the sharp discontinuity of a true shock. Another assumption overturned, another small mystery revealed. The distance at which Voyager 2 crossed the heliopause was about 119 astronomical units from the Sun. That is roughly 11 billion miles. Think about that for a moment. Voyager 2 had to travel for 41 years, at 34,000 miles per hour, just to reach the edge of the sun's wind. 41 years of continuous, silent motion, of covering roughly 300 million miles every year, just across one line in the sand. Now here is where most people, very reasonably, assume the story ends. Voyager 2 crossed the heliopause, so Voyager 2 has left the solar system, right? That is what you see in the headlines. That is what you see in the casual summaries. That is the shorthand. But it is not quite true. Or rather, it is only true if you define the solar system very narrowly, as the region dominated by the sun's particles and magnetic field. If you define the solar system by the sun's gravity, which is arguably a more meaningful definition, then Voyager 2 has barely even started to leave. This is where we need to talk about the Kuiper Belt and the Oort cloud, because these two structures are what truly define the outer limits of our cosmic home. The Kuiper Belt is a region of icy bodies that begins just beyond the orbit of Neptune, at about 30 astronomical units from the Sun, and extends outward to roughly 50 astronomical units. It is where Pluto lives. It is where many other dwarf planets live, objects like Eris and Haumea and Makemake. It contains hundreds of thousands of small icy worlds, leftover debris from the formation of the solar system about 4.5 billion years ago. Voyager 2, at 139 astronomical units, is well beyond the Kuiper Belt. It has flown past that entire region of icy bodies and emerged out the other side. So in terms of the Kuiper Belt, yes, Voyager 2 is gone, but then there is the Oort cloud. And the Oort cloud changes everything. The Oort cloud is a vast, roughly spherical shell of icy objects that surrounds the entire solar system at distances that are genuinely hard to grasp. Its inner edge is thought to begin at around 2,000 astronomical units from the Sun, and its outer edge may extend as far as 100,000 astronomical units, possibly even farther. Some estimates put the outer edge at around 200,000 astronomical units. Let me put that in perspective for you. Voyager 2, at 139 astronomical units, is currently less than 1/10 of 1% of the way to the inner edge of the Oort cloud. Less than 1/10 of 1%. After 48 years of flight. After 13 billion miles. In other words, if we define the solar system by the Sun's gravitational reach, by the region where objects are still bound to the Sun and orbit around it, then Voyager 2 is nowhere close to leaving. At its current speed, it will take Voyager 2 approximately 300 years just to reach the inner edge of the Oort cloud. And then, once it gets there, it will take roughly 30,000 years to cross through the Oort cloud and emerge on the other side truly, gravitationally, free of the Sun. 30,000 years, just across the final shell of our solar system. This is the first time in this story where the scale of what we are talking about really starts to hit home. Because the heliopause, dramatic and meaningful as it was, is a relatively close boundary. The Oort cloud is the real edge. And Voyager 2 is going to spend the next 30,000 years slowly, patiently, silently making its way through a cloud of icy bodies so spread out that the spacecraft will almost certainly never come close to any of them. Here is a way to visualize this. Imagine the entire solar system out to the outer edge of the Oort cloud as a giant soap bubble. The Sun is a pinpoint at the center. The planets, including Earth, are all clustered in the very innermost part of that bubble, huddled close to the Sun like children around a campfire. The Kuiper Belt is a thin ring just outside that campfire circle. And then there is emptiness. Vast, incredible emptiness. And then, far, far out toward the edge of the bubble, there is the Oort cloud, a thin, sparsely populated shell of ice. Voyager 2, right now, is out past the campfire, past the thin ring of the Kuiper Belt, drifting through the emptiness, heading toward that distant shell. It has left the warmth of the fire. It has not yet reached the outer edge of the bubble. It is in the great in-between. Interstellar space. The kind of space that Voyager 2 is now traveling through is not truly empty, but it is almost empty. The density of matter in the interstellar medium is roughly 1 atom per cubic centimeter, on average. Compare that to the air you are breathing right now, which contains something like 27 quintillion molecules per cubic centimeter. The difference is so extreme it is almost impossible to grasp. Interstellar space is more empty than any vacuum we can create in a laboratory on Earth. It's emptier than you can imagine empty being. But even in that emptiness, there are things. Hydrogen atoms, mostly. Some helium. Tiny amounts of heavier elements. Dust grains, scattered and rare, drifting through the void. Magnetic fields, stretched and woven through the gas. Cosmic rays, high-energy particles that have been traveling for millions of years from distant supernovae. Voyager 2 is moving through all of this, slowly, encountering it one atom at a time. Its instruments, while they still function, are measuring this medium, telling us what it is like out there. This is why the 2018 crossing was scientifically so important. For the first time, we had a probe that was actually inside interstellar space, sending back direct measurements of what it was like. And what we learned was fascinating. The interstellar medium is not uniform. It has structure, it has variations in density, in temperature, in magnetic field strength. Voyager 2 is not just crossing empty space. It is crossing a complex, dynamic environment that is shaped by the winds of nearby stars, by the gravity of distant objects, by the relic radiation of ancient cosmic events. Our sun's heliosphere is pushing against this medium like a ship plowing through water, and Voyager 2 has now passed through the hull of that ship. Through the bow wave where the solar wind meets the interstellar gas, and out into the open sea of the galaxy. And yet, despite all of this, despite having crossed this profound boundary, Voyager 2 is still completely, totally, utterly within the sun's gravitational grip. The sun's gravity, although weak at this distance, still shapes Voyager 2's motion. The spacecraft is on an escape trajectory, meaning it has enough speed to eventually break free of the sun's gravity entirely. But that freeing takes a very, very long time. The sun will continue to pull gently on Voyager 2 for tens of thousands of years to come. Even when Voyager 2 finally emerges from the Oort cloud in about 30,000 years, the sun's gravity will still technically have a small influence on its path. Just an increasingly small one. This is one of the strangest facts about the solar system. Gravity reaches very far, much farther than most people realize. The sun's gravity, if you follow it out, does not just end at Neptune or at the Kuiper belt or even at the heliopause. It extends out, weaker and weaker, for more than 1 light year. And the sun's gravitational dominion only ends when the gravity of another star becomes stronger, which happens roughly halfway between our sun and its nearest neighbors. So in one sense, Voyager 2 has left the solar system. It has crossed the heliopause. It is in interstellar space. The solar wind no longer touches it. In another sense, Voyager 2 is still very much at home. The sun still pulls on it. The sun's gravity still shapes its path. The sun is still, at this very moment, the dominant gravitational influence on the spacecraft. Both of these things are true, depending on how you define leaving. There is something poetic about this ambiguity. The boundary between home and not home is not a single line. It is a gradient. It is a slow, layered transition where you cross one edge and then another and then another, and at each edge you are a little bit more gone, a little bit less part of the place you came from. Voyager 2 has crossed the first of these edges. It will cross others in the far, far future, but even after crossing all of them, even after emerging from the Oort cloud tens of thousands of years from now, it will still, in some sense, carry a memory of the sun. It will still be a piece of a solar system object, a piece of something that was born in the disk of gas and dust that became our home. let us talk about what Voyager 2 is actually experiencing. Physically, right now, in this interstellar space. Because the environment out there is strange. The temperature of the interstellar medium in Voyager 2's current location is, paradoxically, both very hot and very cold at the same time. This sounds like a contradiction, but it is not. The individual particles in interstellar space are moving very fast, which by the technical definition means the gas is hot. Some estimates put the kinetic temperature of the surrounding gas at several thousand degrees, but because there are so few particles per cubic centimeter, the total amount of heat that can be transferred to any object is vanishingly small. Voyager 2 itself, physically, is extremely cold, probably somewhere around minus 450 degrees Fahrenheit, just barely above absolute zero. It is a cold object drifting through a technically hot but incredibly thin gas. If you were out there, you would freeze almost instantly. Not burn. Even though the gas around you has individual particles moving at thousands of miles per second. The darkness is also worth contemplating. Out where Voyager 2 is, the sun is still the brightest object in the sky, but it is no longer a disk. It is just a point of light. From Voyager 2's perspective, the sun would appear as an unusually bright star, but still just a star. The warmth, the heat, the dominance the sun has had over Voyager 2's entire journey until recently is fading. It is becoming just another star among many. And for the first time in the spacecraft's existence, the light of other stars is becoming, in a real sense, competitive with the light of our own. This is what it means to be in the space between. Voyager 2 is in a region where the sun's grip is loosening but not gone, where the galaxy's influence is growing but not dominant, where the old environment has been left behind, but the new environment has not yet been fully entered. It is in transition. It will be in transition for thousands and thousands of years. And what is especially humbling is that this transition, dramatic as it sounds, is happening at a speed that, in galactic terms, is almost stationary. 34,000 miles per hour is, as we have said, incredibly fast by human standards. But interstellar space is so vast that even at that speed, progress is almost imperceptible when measured against the scale of the galaxy. Voyager 2 is crawling. It is inching. It is taking its tiny, slow steps across a sea so wide that even a million years of such steps will barely register. This is what sets up everything that comes next. Because once you understand that Voyager 2 has crossed one boundary but still has tens of thousands of years of slow travel ahead of it, just to fully leave the sun's gravitational reach, you start to realize something uncomfortable. If it takes 30,000 years just to cross the Oort cloud, what does 1 million years of flight actually mean? How far does Voyager 2 really travel in that time? And more importantly, how does that distance compare to the distances that separate stars from each other, galaxies from each other, and the true scales of the universe? The answer, as we will see, is both astonishing and deeply humbling. Voyager 2 will travel a distance in 1 million years that is, by any human measure, incomprehensibly vast. And yet, by the measure of the galaxy itself, that same distance is almost nothing. It is less than the length of a single street in a city the size of the Milky Way. It is the tiniest, quietest, most modest stroll through a neighborhood so large that we barely understand its geography. But before we get to those scales, sit with this for a moment. Voyager 2 right now is in interstellar space. It has crossed the heliopause. It is tasting the galaxy for the first time, feeling the gentle pressure of its magnetic fields, the whisper of its gas, the faint cosmic rays from distant supernovae. And yet, it is still gravitationally a child of the sun, still being pulled ever so slightly by the star that made it, still technically inside the gravitational halo of our system. It is both gone and not gone. It is both home and away. It has crossed a line, but the line was not where most of us thought it was. The real line, the gravitational edge, is still 30,000 years ahead of it. And when you start to think about what 30,000 years of flight looks like, and then scale that up to 1 million years, the full, staggering, beautiful, terrifying emptiness of interstellar space begins to come into focus. That is where we go next. Into the scale problem. Into the question of what distance really means when you are moving this slowly through something this large. Because the truth about 1 million years of flight is not what most people expect. It is far stranger and far lonelier and far more awe-inspiring than the simple numbers suggest. Now we arrive at the question that sits at the heart of everything. If Voyager 2 is moving at roughly 34,000 miles per hour, and if we let it fly for 1 million years, where does it actually end up? How far does it actually go? And what does that distance mean in the context of the galaxy that surrounds it? The math is simple, the implications are not. Let us do the calculation together, slowly, because the numbers themselves tell a story that is almost impossible to feel without walking through them step by step. Voyager 2 travels about 300 million miles every year at its current speed. In 1 million years, that adds up to 300 million multiplied by 1 million. The result is 300 trillion miles. 300 trillion. Write that out. 300,000 billion miles. It is a number so enormous that it ceases to mean anything to a human mind. You cannot picture 300 trillion miles. Nobody can. Your brain simply refuses. So let us translate it into a unit that makes more sense at cosmic scales. The light year, which is the distance that light travels in 1 year, is approximately 5.88 trillion miles. If you divide 300 trillion by 5.88 trillion, you get roughly 17. So Voyager 2, after 1 million years of continuous flight at its current speed, will have traveled about 17 light years. 17 light years. Let that sit for a moment. After a full million years of flight, after a span of time so long that every human civilization that has ever existed could rise and fall hundreds of times over, this spacecraft will have traveled 17 light years. Now, 17 light years sounds impressive if you have never thought about cosmic distances before. And in truth, it genuinely is impressive. It is an enormous distance by any human standard. It is a distance no human-built object has ever traveled in any meaningful span of time before. It is worth noting, though, that Voyager 2 is no longer the fastest human-made object, and has not been for some time. That might surprise you. The spacecraft that most people associate with deep space travel is not actually the speed champion. Other probes, built decades later, have reached considerably higher velocities. The Parker Solar Probe, launched in 2018, has at times moved at more than 430,000 miles per hour as it loops close to the Sun, using solar gravity to accelerate itself to breathtaking speeds. New Horizons, the probe that flew past Pluto in 2015, left Earth at a higher launch velocity than Voyager 2 did, although it is now traveling somewhat slower than Voyager 2 through interstellar space because it did not get the same sequence of gravity assists. But here is the interesting thing. Even those faster probes do not meaningfully change the scale problem. The Parker Solar Probe, impressive as it is only fast when it is near the Sun. Its average speed as it travels away from the inner solar system is nowhere near its peak. And even if some future spacecraft could maintain the Parker Solar Probe's peak speed continuously, moving at 430,000 miles per hour for a full million years, it would only cover about 220 light years in that time. Still less than 1% of the galaxy's diameter. The problem is not that our spacecraft are slow. The problem is that the galaxy is genuinely, unimaginably large. To reach a nearby star in a time frame that relates to human lifetimes, you would need to move at a significant fraction of the speed of light. If you could travel at 10% of light speed, which is about 67 million miles per hour, roughly 2,000 times faster than Voyager 2, you could reach Proxima Centauri in about 42 years. That is a journey a human could, in principle, live through. But reaching 10% of light speed requires an amount of energy so vast that no propulsion system we know how to build can provide it. Theoretical concepts like laser-pushed light sails, nuclear pulse propulsion, or antimatter drives have all been proposed. None of them have ever been built. None of them are close to being built. The engineering challenges, the energy requirements, the material science problems all remain beyond us. And even if we could build such a ship, 10% of light speed is still only fast enough to reach our nearest stellar neighbor in a single human lifetime. The rest of the galaxy remains, for all practical purposes, out of reach. But the moment you compare it to the scale of the galaxy around it, 17 light years starts to look almost laughably small. Because the Milky Way galaxy, the place where all of this is happening, is about 100,000 light years across. 100,000. Voyager 2, in 1 million years of flight, will have crossed about 1 part in 6,000 of the galaxy's width. It will have made it roughly 0.017% of the way across our own cosmic home. That is less than 1/50th of 1%. Less than the width of a single hair compared to the length of a football field. That is what 1 million years of continuous interstellar flight at 34,000 miles per hour gets you when measured against the scale of the galaxy. This is the scale problem. And it is not a problem of Voyager 2 being slow. It is not a problem of our engineering being primitive. It is a problem built into the fundamental geography of the universe. Space out there between the stars is so large that almost nothing we can imagine covers any meaningful fraction of it, in any meaningful span of time. Let me try to make you feel this in a different way. Imagine you are walking across a continent. Imagine you are walking from one coast of the United States to the other, from the Atlantic to the Pacific. That journey at a normal walking pace would take you about 6 months of steady walking. Now imagine that Voyager 2 is a walker, and the Milky Way is your continent. Except the continent is not the United States. It is a continent 100,000 miles across. And Voyager 2, our tireless walker, is moving slowly enough that in 1 million years it covers only about 17 miles of that continent. 17 miles out of 100,000. You could drop our walker down somewhere in this continent-sized galaxy, and after 1 million years, you would not be able to find it on any map. Its starting position and its ending position would look like the exact same point at that scale. The movement would be invisible. That is what 1 million years of Voyager 2's flight actually looks like when you draw it on a map of the galaxy. And here is where the story gets even more humbling. Because 1 million years is already an almost unimaginable span of time by human standards. All of recorded history, every civilization that has ever written anything down, every king, every queen, every war, every discovery, every cathedral, every song, every poem, fits into the last 5,000 or 6,000 years. 1 million years is more than 150 times longer than all of that. 1 million years ago, our ancestors were not even fully human in the modern sense. Homo sapiens, our species, only emerged about 300,000 years ago. 1 million years takes you back past our species entirely, back to earlier hominids who were still figuring out fire and basic tools, and yet, even a span of time that long, a span that encompasses the entire history of our species and more, is not enough for Voyager 2 to cross any meaningful fraction of the galaxy. This is where you really start to feel the strangeness of the universe. Speed and distance at this scale stop working the way they do on Earth. On Earth, if you can move fast, you can cover the planet. A commercial jet at 600 miles per hour can circle the entire globe in about 42 hours. A rocket moving at 17,000 miles per hour in low Earth orbit can circle the planet every 90 minutes. On Earth, speed conquers distance. That is the lesson of human transportation history. Make it go faster, and you can go farther. But in interstellar space, that lesson breaks. Voyager 2 is going extraordinarily fast by any human measure. It is going more than 50 times faster than a jet airliner. And yet, after 1 million years, it has barely moved. The ratio of its speed to the distances involved is so small that even one of the fastest spacecraft humanity has ever built, given a span of time longer than all of human evolution, cannot cross the galaxy. Cannot even begin to cross it, cannot even cross a noticeable fraction of it. To really understand why, you have to grasp what a light year is, and you have to feel it, not just know it as a number. A light year is the distance that light travels in 1 year. Light, which is the fastest thing in the universe, moves at about 186,000 miles every second. Every second. In 1 second, light could circle the Earth 7.5 times. In 1 minute, it could travel from the Earth to the Sun several times over. In 1 year, it covers nearly 6 trillion miles. That is a single light year. And the nearest star to our Sun, a small red dwarf called Proxima Centauri, is 4.24 light years away. Which means that Voyager 2, given a full 1 million years, would only travel about 4 times that distance before running out of our 1 million year window. And Proxima Centauri is our closest stellar neighbor. Most stars are much, much farther. Think about what this means. If you could somehow aim Voyager 2 directly at Proxima Centauri, and if that star were somehow frozen in place and not moving, it would still take Voyager 2 approximately 75,000 years to reach it. 75,000 years of continuous flight just to reach our nearest stellar neighbor. And Voyager 2 is not aimed at Proxima Centauri. Its trajectory points in a completely different direction, toward a region of sky that contains no nearby stars worth mentioning. So when we say that Voyager 2 travels about 17 light years in 1 million years, what we are really saying is that it covers a distance equivalent to about 4 times the gap to the nearest star. That sounds like a lot. Until you remember that there are roughly 400 billion stars in the Milky Way, and that they are separated from each other on average by distances of several light years. Voyager 2's million-year journey will take it through a handful of star systems worth of distance out of a galaxy that contains hundreds of billions of stars spread over 100,000 light years of space. Let us think about what those 17 light years actually contain. If you drew a sphere around Voyager 2's future position with a radius of 17 light years from its current location, how many stars would you find in that volume of space? The answer is surprisingly small. Within 17 light years of our own sun right now, there are only about 50 known stellar systems. 50. That is it. And most of those are red dwarfs, small dim stars that are completely invisible to the naked eye. The famous stars you might know, the bright ones that form constellations, are almost all farther away than that. Sirius, the brightest star in our night sky, is 8.5 light years away. Vega, the bright blue star you can see in summer, is 25 light years away. Just outside the sphere Voyager 2 will traverse. Betelgeuse, the red giant that forms Orion's shoulder, is roughly 500 light years away. Almost 30 times more distant than Voyager 2 will reach in a million years. So the region Voyager 2 will explore, if we can even call it exploration, is a very small, sparsely populated bubble of our galactic neighborhood. It will pass through space that contains only a handful of stars, most of them dim red dwarfs, and most of them too far from its trajectory to matter much. This is the reality of the galactic neighborhood. The stars are rare. The space between them is overwhelming. A million years of travel, impressive as that sounds, covers only a tiny corner of a region that is itself a tiny corner of a much larger region that is itself a tiny corner of the galaxy. And the emptiness is so complete that Voyager 2 will, almost certainly, never collide with anything significant during its journey. Space is not just empty in the sense that there are no planets or stars along its path. It is empty in a deeper sense. The chance of Voyager 2 striking even a dust grain large enough to damage it is incredibly small over the timescales we're discussing. The interstellar medium does contain dust, but it is sparse enough that a spacecraft the size of a small car can cross vast distances without encountering anything substantial. Over millions of years, Voyager 2 will likely accumulate some erosion from micro-impacts with interstellar dust particles, but nothing catastrophic. It will keep its shape. It will keep its integrity. It will keep moving, undisturbed, through a void so empty that human intuition has no equivalent for it. There is a concept in astrophysics called the mean free path, which is the average distance a particle travels before encountering another particle. In the densest parts of Earth's atmosphere at sea level, the mean free path is measured in nanometers. In interstellar space, the mean free path of a spacecraft-sized object avoiding any significant collision is measured in light years, possibly many light years. Voyager 2 could travel for millions of years through this environment, without ever bumping into anything that matters. So when we picture Voyager 2's journey, we should not imagine it weaving through a crowded stellar field, dodging stars and planets and debris. We should imagine it gliding through an ocean so empty, so quiet, so vast that it essentially never encounters anything at all. Just the occasional atom of hydrogen, the occasional dust grain, the occasional whisper of a magnetic field from a distant star. Nothing more. Here is one more way to try to feel this. Imagine shrinking the Milky Way down to the size of North America. The whole galaxy, all 400 billion stars, all the spiral arms, all the gas and dust and dark matter, compressed to the scale of a continent you could drive across. In that shrunken galaxy, the distance Voyager 2 travels in 1 million years would be equivalent to walking a few miles. A few miles on a continent thousands of miles across. You would not even have left your starting state. This is why speed, at cosmic scales, becomes almost meaningless. It is not that Voyager 2 is slow in any absolute sense. It's that space is unimaginably, absurdly, almost grotesquely large. Large in a way that human intuition cannot handle. Large in a way that makes every achievement of human engineering, every rocket we've ever built, every probe we have ever launched, look like a child splashing in the shallow end of an ocean that extends beyond the horizon in every direction. And yet, there is something strangely beautiful about this, because it tells us something fundamental about the universe we live in. The spaces between things out there are not like the spaces between things on Earth. On Earth, you can cross any distance you want to cross, given enough time and determination. People have walked across continents. People have sailed across oceans. People have flown around the world. There is no place on Earth you cannot reach. But the spaces between stars are different. They are not distances that are simply larger. They are distances of a fundamentally different kind. They are distances that laugh at our speed. Distances that mock our engineering. Distances that refuse to be conquered by anything we can currently imagine. And Voyager 2, that small 1970s spacecraft, is our one serious attempt to cross them. Not to arrive anywhere, not to reach any particular destination, just to go, to move outward, to spend the next million, 10 million, 100 million years patiently, silently, coldly crossing the void. Let us think for a moment about what the emptiness actually looks like along Voyager 2's path. Because it is important to understand that the space Voyager 2 is traveling through is not a space filled with obstacles. It is not like driving through a crowded city. It is emptiness beyond emptiness. The average distance between stars in our region of the galaxy is several light years. In a volume of space as big as, say, 5 light years across, there might be 1 or 2 stars, and then vast oceans of nothing in between. A star is a huge object by human standards. Our sun is about 865,000 miles across. That sounds enormous, but compared to the distance to the next star, which is more than 25 trillion miles away, the sun is tiny. If you shrunk the sun to the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. 4 miles of absolute emptiness between 2 grains of sand. That is roughly the density of stars in our part of the galaxy. That is the kind of space Voyager 2 is crossing. So when Voyager 2 travels 17 light years in 1 million years, it is moving through a medium that is, for all practical purposes, completely empty. It will not pass near any stars. It will not encounter any planets. It will not run into any significant collection of matter. It will simply glide undisturbed through the cold thin gas of the interstellar medium for millennium after millennium after millennium, with nothing to mark its progress except the slow, steady increase in the distance behind it. There is another way to think about this scale problem, and it involves imagining what we would need to actually cross the galaxy. Because the honest answer is that, at Voyager 2's speed, crossing the Milky Way would take something on the order of 2 to 3 billion years. That is not a typo. Billion. With a B. At 34,000 miles per hour, to cross 100,000 light years, Voyager 2 would need roughly 2 billion years. 2 billion years is a span of time longer than the existence of complex multicellular life on Earth. 2 billion years ago, life on our planet consisted of single-celled organisms floating in the oceans. If you had launched a Voyager-style spacecraft 2 billion years ago, and it had been flying at 34,000 miles per hour continuously ever since, it would just now be finishing its trip across the galaxy. Just now. After 2 billion years. That is the scale we are dealing with. And yet, and this is where the strangeness deepens, Voyager 2 will keep going. It will not stop. It is not going to hit anything. It is not going to be captured by anything. It is not going to slow down in any meaningful way for an extremely long time. So while 1 million years of flight only covers 17 light years, Voyager 2 will eventually cover more. In 10 million years, about 170 light years. In 100 million years, about 1,700 light years. In a billion years, about 17,000 light years. In 10 billion years, a number longer than the current age of the universe, about 170,000 light years, which would finally exceed the width of the Milky Way. But wait, the universe is not 10 billion years old yet. Our planet is only about 4.5 billion years old. The sun will exhaust its hydrogen fuel and begin to die in about 5 billion years. So even if Voyager 2 kept going with perfect efficiency for the rest of the sun's life, it would not have time to cross the galaxy. The sun that made it would die before the spacecraft had finished even its home galactic neighborhood. This is the real, humbling truth about interstellar distance. On the timescales, we can actually build machines that function and send them out and watch them travel. Even the biggest numbers we can imagine do not get us very far. The galaxy is simply too large. The distances are simply too great. Our speeds, even our best speeds, are simply too slow. And now you start to see why the original title question, where will Voyager 2 be in 1 million years, is such a strange question. Because the honest answer is, it will be almost exactly where it is right now, in galactic terms. It will have moved about 17 light years from its current position. It will still be in the same small neighborhood of our galaxy. It will still be in the same general region of the Orion arm, the minor spiral arm where our sun lives. It will not have traveled to the core of the galaxy. It will not have approached the far side. It will not have left the neighborhood. It will not even have come close to leaving the neighborhood. It will just be drifting, still, through the same small corner of the Milky Way that we currently occupy. 17 light years in some particular direction from where it is now. This is the most humbling realization in this entire story. We often imagine that given enough time, any journey is possible. Given 1 million years, surely you can go far. Given 1 million years, surely you can cross oceans of space. But no, not when the oceans are this big. Not when the container is this vast. 1 million years is not enough. 100 million years is not enough. Even 1 billion years is not enough to cross our home galaxy at the speed of Voyager 2. There is a kind of philosophical weight to this realization, and it is worth sitting with. Voyager 2 represents in many ways humanity at its best. It is a machine built by human hands, powered by human ingenuity, carrying human messages to the stars. And yet, even this best effort, even this most impressive of our interstellar envoys, cannot really cover any meaningful fraction of the galaxy in any time span that relates to human experience. The universe is genuinely fundamentally not built for our timescales or our speeds. And yet, this is not a reason for despair. It is a reason for awe. Because Voyager 2 is going, it is moving. It is, right now, steadily, quietly, covering those 300 million miles per year. It is not standing still. It is not giving up. It is simply accepting the scale of the universe and doing what it can within that scale. In 1 million years, it will have covered 17 light years. That is not nothing. That is, in fact, an astonishing achievement for a machine the size of a small car, built in the 1970s, running on decaying plutonium. 17 light years is an incredible distance. It just happens to be vastly less than the galaxy is large. One more thought experiment. To really drive this home, consider the light that is leaving Earth right now, this very second. Light from your city, light from the sun as it reflects off our oceans, light from every point on our planet. That light is heading out into space in every direction. It is moving at the speed of light, which is hundreds of thousands of miles per second. In 1 million years, that light will have traveled 1 million light years. It will have gone through our galaxy and crossed most of the distance to the Andromeda galaxy, our nearest large neighbor. Voyager 2, in the same 1 million years, will have traveled 17 light years. Light in that span will have gone roughly 60,000 times farther than Voyager 2. 60,000! And even light, as fast as it is, still takes millions of years to cross from one galaxy to another. Even light, the fastest thing in the universe, is slow compared to the distances between galaxies. If even light is slow, what chance does a small spacecraft moving at 34,000 miles per hour have? The answer is that it has no chance of crossing the galaxy in any meaningful time span. And that is okay, because Voyager 2 is not trying to cross the galaxy. Voyager 2 is just going. It is existing. It is moving. It is being out there as a small piece of human civilization, drifting through interstellar space for timescales that will outlast our species, our planet, and possibly even our sun. But there is one more complication we have to address before we can answer the question of where Voyager 2 will be in 1 million years. Because so far, we have been talking about Voyager 2 as if it is moving through a galaxy that is standing still, as if the stars around it are fixed in place, as if the reference points we use to measure its position are permanent. They are not. Stars move. All of them. Our sun moves. The stars we see in the night sky move. The entire galactic neighborhood is in motion, orbiting the center of the Milky Way, drifting relative to each other, slowly changing their positions over spans of time just like the one we are considering. In 1 million years, the sky itself changes. The stars that are close to us now will not be close to us then. Some stars will have drifted away. Other stars, currently far, will have come closer. The geography of our neighborhood is not frozen. It is alive, and it is changing. This means that when we ask where Voyager 2 will be in 1 million years, we are asking about a moving target in a moving landscape. The spacecraft is drifting, yes, but everything around it is also drifting. And in the final piece of our story, we have to confront what that means. Because it turns out that Voyager 2, despite its slow crawl, will actually have a close encounter with another star. Not in 1,000 years, not in 10,000, but in roughly 40,000 years from now, Voyager 2 will pass within a few light years of a small, dim red dwarf called Ross 248. And that close approach and what it tells us about Voyager 2's true place in the galaxy is the final piece of this strange, beautiful, humbling puzzle. Here's the thing nobody tells you about Voyager 2 until you really start to understand the geography of the galaxy. When we ask where it will be in 1 million years, we're asking a question that, on the surface, seems to have a simple answer. Just take its speed, multiply by the time, draw a straight line, and there you go. Point A to point B. Done. But the universe does not work that way. The galaxy does not sit still while Voyager 2 drift through it. Every single star in our neighborhood, including our own sun, is moving. And those motions, slow as they are by human standards, change everything about how we think about Voyager 2's journey. Stars are not fixed. This is one of the hardest ideas for the human mind to accept, because when you look up at the night sky, the stars seem so permanent. The constellations you see tonight are the same constellations your grandparents saw. The same constellations the ancient Greeks saw. The same constellations the earliest human astronomers mapped out tens of thousands of years ago. The stars appear, for all practical purposes, eternal, fixed, nailed to the sky, but they are not. They are moving, all of them, at incredible speeds, in different directions, orbiting the center of the Milky Way on paths that take hundreds of millions of years to complete. Our own sun, for example, is carrying us around the galactic center at roughly 483,000 miles per hour, more than 14 times faster than Voyager 2. But relative to the stars in our immediate neighborhood, those stars are all moving along with us in similar orbits. So the sun's motion relative to them is much slower, only about 27,000 miles per hour. That smaller relative motion is what matters when we ask where Voyager 2 ends up compared to nearby stars. It takes about 230 million years for the sun to complete one lap around the galaxy. The last time the sun was in its current position relative to the galactic center, dinosaurs were just beginning to evolve on Earth. The time before that, there were no complex animals yet. Our sun has made roughly 20 such laps since it was born, 4.5 billion years ago. And every other star in our neighborhood is doing the same thing. All of them are moving. Some are moving roughly with us, in similar orbits. Others are moving differently, drifting toward or away from us at various angles and speeds. The result is that the pattern of stars around us, the shape of our stellar neighborhood, is constantly, slowly, imperceptibly shifting. Over 1 million years, that shift becomes very noticeable. Stars that are near us now will have moved. Stars that are currently far will have drifted closer or farther. The sky itself, seen from Earth, would look meaningfully different 1 million years from now. The constellations we know today would be distorted, broken, reformed into new patterns we would not recognize. This matters enormously for Voyager 2. Because Voyager 2 is not aimed at any particular star, its trajectory is simply the direction it happened to be heading when it left the solar system. And as it drifts through space, the stars around it are also drifting. Some of them will happen to drift closer to Voyager 2's path. Some will drift farther away. The geometry of its journey is not a simple straight line through a static map. It is a slow, complicated dance of a moving object through a moving landscape. Here's where one of the most remarkable predictions in all of space exploration comes in. Astronomers, by carefully measuring the motions of nearby stars and combining that with the Voyager 2's trajectory, have been able to project what its future encounters will look like. And the result is genuinely beautiful. In approximately 40,000 years from now, give or take a few thousand, Voyager 2 will pass within about 1.7 light years of a small, dim red dwarf star called Ross 248. Ross 248 is not a famous star. Most people have never heard of it. It is about 10.3 light years away from us right now. Visible only with a telescope, far too faint to see with the naked eye. It is a tiny red dwarf, much smaller and cooler than our Sun, the kind of star that burns very slowly and lives for hundreds of billions of years. It is not particularly special in any cosmic sense, but it is moving. And in about 40,000 years, its motion and Voyager 2's motion will bring them into a relatively close encounter. Not a collision, not even close to a collision, but by the standards of interstellar distances, an almost intimate passage, 1.7 light years. That is the closest Voyager 2 will come to any star for an extremely long time. And it is worth pausing to think about what 1.7 light years actually means. That is roughly 10 trillion miles. It is much more than 4,000 times the distance Voyager 2 has traveled so far. And yet, in galactic terms, it is a whisper-close encounter. The kind of approach that, if you were watching from a cosmic perspective, would look like two small objects barely brushing past each other in the vastness of an enormous ocean. And here is the strange part. Ross 248 will not be where it is now when this happens. At this very moment, Ross 248 is 10.3 light years from the Sun, but the star is moving in our general direction. It is actually approaching the solar system, slowly, and in about 36,000 years from now, it will temporarily become the closest star to our Sun, passing within about 3 light years of us. For a few thousand years, Ross 248 will hold the title of our nearest stellar neighbor, displacing Proxima Centauri from that role. Ross 248 itself is worth knowing about, even though it is obscure. It is what astronomers call a flare star, a small red dwarf that occasionally brightens dramatically in brief, violent bursts of activity. These flares release enormous amounts of radiation, sometimes doubling or tripling the star's brightness for a few minutes before it settles back down. If Ross 248 has any planets, which we do not currently know, they would have a difficult time hosting life because of this stellar violence. The star itself has only about 12% of the Sun's mass, and emits only a tiny fraction of the Sun's light. It is dim, unassuming, and yet it happens to be the star that Voyager 2 will come closest to for an extremely long time. From Voyager 2's perspective, during the close approach, Ross 248 would appear as the brightest object in the sky, brighter than any star would appear from Earth. But even at its closest approach, 1.7 light years away, the star would still be just a point of light, not a disk. The spacecraft would not be close enough to see any detail, only to register a particularly bright point against the background of other, more distant stars. Our Sun, meanwhile, would appear as a relatively faint star, far dimmer and less prominent than the star it was passing. For that brief moment in cosmic time, Voyager 2 would essentially be a tiny interstellar traveler with a new, temporary guide star, before continuing on into the deeper dark. After Ross 248, Voyager 2's next notable stellar encounter, far less close, will not come for hundreds of thousands of years more. It will eventually drift past other faint stars at distances of several light years, None of them close enough to matter physically, but each representing a tiny moment of temporary stellar companionship in an otherwise solitary journey. And during that period of approach, Voyager 2, which has been drifting outward from the sun all along, will be in a position to make its close pass. Think about the beauty of that coincidence. Voyager 2 was launched in 1977, aimed in a particular direction for reasons that had nothing to do with Ross 248. The engineers at JPL were not thinking about that star. They were thinking about Jupiter, Saturn, Uranus, and Neptune. The trajectory was chosen for planetary science. And yet, by pure accident of geometry and motion, Voyager 2 happens to be moving in roughly the right direction, and Ross 248 happens to be moving in roughly the right direction. That their paths will bring them within a couple of light years of each other 40,000 years from now. Now, 1.7 light years is not close enough for anything dramatic to happen. Voyager 2 will not be captured by Ross. 248's gravity. It will not orbit the star. It will not be deflected in any significant way. The star's gravitational influence at that distance is too weak to do anything noticeable to the spacecraft. Voyager 2 will simply pass through the outer reaches of Ross, 248's gravitational sphere largely unaffected, and continue on its way. But for a brief moment in cosmic time, for a few thousand years centered on that point of closest approach, Ross 248 will be the dominant star in Voyager 2's sky. Our sun, at that point, will be more distant, a dim reminder of the home it left behind. And then, Voyager 2 will keep going, moving past Ross 248, outward and onward, into deeper regions of the galaxy. And this is where the original question, where will Voyager 2 be in 1 million years, gets its real answer. Not a precise, dramatic, pin-on-a-map answer, but an honest one. An answer that respects the scale of space and the motion of stars. In 1 million years, Voyager 2 will be approximately 17 light years from where it is right now. That position, relative to our current sun, will be in a particular direction toward the southern sky, roughly in the region of the constellation Parvo. But here's the thing. Our sun itself will have moved in that same million years. The sun will have traveled about 483,000 miles per hour, multiplied by 1 million years, which works out to about 70 light years of motion. The sun, in a million years, will be 70 light years away from its current position. Nearby stars, including Ross 248, will also have moved on their own paths. So the honest answer is this. In 1 million years, Voyager 2 will be in a general region of the Milky Way no longer particularly close to the sun that made it, but nowhere near the far side of the galaxy, the galactic core, or anywhere particularly dramatic. It will be drifting, alone, through a small region of the Orion Arm. It will have passed by Ross 248 long ago, some 960,000 years earlier. It will not have had another close stellar encounter of any significance. It will simply be in the emptiness between stars, far from any meaningful reference point, still moving, still cold, still silent, and the exact precise position cannot be known. That is the other part of the honest answer. Over 1 million years, the accumulated uncertainties in Voyager 2's trajectory and in the motions of the stars around it mean that we cannot say exactly where it will be. We can say roughly. We can say within a certain region. But we cannot place a precise pin on a cosmic map and say, here, this spot, This is where the spacecraft will be. The uncertainties grow with time. Our knowledge of stellar motions is good but not perfect. Our knowledge of tiny gravitational tugs from distant objects is incomplete. After 1,000,000 years, these small uncertainties add up to something like a large region of space where Voyager 2 is likely to be, but not a single precise location. This is, in some ways, a beautifully appropriate ending for this story, because Voyager 2 was never meant to arrive anywhere. It was never aimed at a destination. It was never going to land on a planet or orbit a star or accomplish a specific interstellar goal. It was simply built to fly, to do its work at the outer planets, and then to keep going afterward, a message in a bottle cast into the cosmic sea. And like any message in a bottle, its final position depends on currents and winds we cannot fully predict. We know it is out there. We know it will keep going. We know roughly where it will be. But the exact spot, the precise coordinates, cannot be pinned down over timescales this long. There is something profound about accepting this uncertainty. We like precise answers. We like to know exactly where things are. But the universe, over 1,000,000-year timescales, does not give us precise answers. It gives us regions. It gives us probabilities. It gives us ranges. Voyager 2, in 1,000,000 years, will be somewhere in a vast region of space, drifting through the emptiness, carrying its golden record and its aging electronics and its silent systems, a piece of human civilization no longer really tied to any specific location. And even more humbling, that uncertainty grows with every additional 1,000,000 years. In 2,000,000 years, the uncertainty about Voyager 2's position will be larger still. In 10,000,000 years, even larger. In 10,000,000 years, even larger. In 100,000,000 years, the uncertainty might be so great that we could only say Voyager 2 is somewhere in a large fraction of the galactic disk. The spacecraft itself will keep moving with perfect mechanical precision, but our ability to predict where that motion will take, it fades as time goes on. The galaxy is too dynamic, too complicated, too full of small gravitational influences for us to project its path indefinitely. And what about the spacecraft itself, physically, over these enormous timescales? What happens to a piece of metal and plastic and circuitry that drifts through interstellar space for millions of years? The answer is, remarkably, very little. Voyager 2 will slowly accumulate microscopic damage from cosmic rays, high-energy particles that sleet through space from distant supernovae, and other violent cosmic events. Over millions of years, these particles will gradually degrade the spacecraft's electronics, though the electronics will have long since ceased to function anyway. The outer surfaces will be slowly eroded by impacts with interstellar dust, though at rates so slow that the erosion will be measured in microns per 1,000 years or so. The golden record, the 12-inch gold-plated copper disc attached to the side of each Voyager spacecraft, is expected to survive for an extraordinarily long time. The gold plating is chemically inert and will not tarnish or corrode in the vacuum of space. The grooves that contain the recorded information are etched into the copper and protected by the gold layer. Estimates suggest the record could remain readable for more than 1,000,000,000 years, possibly several billion, before cosmic ray damage and micrometeorite impacts degrade it beyond recovery. Think about that. 1,000,000,000 years. The record itself will likely outlast the sun, outlast the Earth, outlast any biological trace of our species. This is what makes Voyager 2 so strange and so moving. It is, in its own quiet way, an attempt at a kind of immortality. Not for any individual human, but for the species as a whole. The people who built it knew that it would leave the solar system. They knew it would drift among the stars. They knew that barring some unimaginable cosmic accident, it would simply keep going for timescales that dwarf everything else humans have ever made. And so they attached the golden record, and they included greetings and music and images, not because they expected anyone to find it, but just in case. Just in the tiniest, most improbable chance that someday, somewhere, something might encounter this small piece of us and know that we existed. This is the strange, quiet truth about interstellar travel. It is not that the destination matters. It is that the act of going is what defines the object. Voyager 2 is not going anywhere in particular. It is just going. And that going, that steady, relentless, beautiful motion outward, is what makes it what it is. Let me try to give you one last image that might help you hold all of this in your mind at once. Imagine a small, cold piece of metal about the size of a small car, drifting through the emptiness between stars. Its transmitters have long since gone silent. Its instruments are long since powered down. Nobody on Earth has heard from it in nearly 1 million years. The engineers who built it, the mission controllers who operated it, the scientists who analyzed its data, the people who watched its launch on television, the people who grew up knowing it was out there. All of them have been gone for countless generations. The Earth itself has changed. The species that built the spacecraft may no longer exist, or may have evolved into something very different, or may have left the planet entirely. The sun that gave the spacecraft its original trajectory has moved 70 light years from where it was on the day of launch. Everything about the context in which Voyager 2 was built is gone. And yet, Voyager 2 itself is still there, still moving, still cold, still silent, still carrying on its side the golden record with its greetings in dozens of human languages, its music from around the world, its images of our planet and our species. It is still there, in some region of space, roughly 17 light years from where its sun now sits, drifting through the emptiness between stars, a tiny, permanent piece of a civilization that may or may not still exist. That is where Voyager 2 will be in 1 million years. Not somewhere dramatic, not on a distant planet, not orbiting a new star, just out there, alone, silent, moving. A small metal object in the vast darkness, still doing what it was set in motion to do because nothing has ever stopped it, and nothing ever will. And there is one more thought I want to leave you with, because I think it captures something essential about this whole journey. Voyager 2 is, in a very real way, the longest-lived artifact humanity has ever created. Not in the sense that it has existed for the longest time, because many of our monuments and structures on Earth are much older, but in the sense that it will continue to exist, essentially unchanged, for timescales that will dwarf every human achievement by enormous factors. Buildings on Earth will crumble, languages will evolve beyond recognition, civilizations will rise and fall, even the continents themselves will rearrange through plate tectonics. Mountains will erode, oceans will shift. In the far, far future, perhaps even the Earth itself will be consumed when the sun dies and expands into a red giant. All of that will happen. All of that is coming. None of it can be stopped. But Voyager 2 will still be out there. In 1 million years, it will still be out there. In 100 million years, it will still be out there. In 1 billion years, still out there. In 5 billion years, when the sun dies and Earth is destroyed, Voyager 2 will almost certainly still be out there, floating through interstellar space, by then having crossed some meaningful fraction of the galaxy, its golden record still attached to its side, its metal body still cold, its circuits still silent. Long after every trace of us on Earth is gone, Voyager 2 will continue. It is the closest thing we have ever made to something permanent, and it is drifting, right now, through the space between stars, carrying a memory of us into a future we cannot imagine. So when you look up at the night sky tonight, toward the southern part of the sky, toward the direction of the constellation Telescopium, know that somewhere out there, in that direction, at a distance that no human will ever cross in any lifetime we can conceive of, a small piece of our civilization is moving. It is moving silently. It is moving steadily. It is moving at 34,000 miles per hour through a medium that is, for all practical purposes, empty. It is carrying with it our greetings, our music, our images, our hopes. It has no destination. It has no arrival. It just has the going. And in 1 million years, it will still be going. In a small region of the galaxy, not so very far from where it is today, by galactic standards, but impossibly far by human ones. It will have drifted 17 light years from its current position. It will have had one close encounter with a star named Ross 248, long in its past by then, and it will be alone, moving, silent, cold, continuing the journey that we started for it nearly 50 years ago. That is where Voyager 2 will be in 1 million years, not arriving anywhere, not reaching a destination, just going forever through a galaxy that is, for reasons built into the fabric of space itself, almost infinitely larger than any single journey can cover. And that, maybe, is the most beautiful answer of all, because it tells us something about the universe we live in. It tells us about scale. It tells us about patience. It tells us about the strange, humbling fact that even our best, fastest, most determined efforts to reach out into the cosmos result in a slow, lonely drift through a tiny corner of an enormous galaxy. And yet, somehow, that drift is enough. It is enough for Voyager 2 to exist. It is enough for it to keep going. It is enough for it to carry our messages, forever, into a future that has no end in sight. The spacecraft that refuses to stop will not stop. Not in 1,000 years, not in 1,000,000, not in 1,000,000,000. It will just keep going, in the dark, between the stars, a permanent, silent monument to the moment our species first reached out beyond our own home and dared to send something into the space between worlds. And that, in the end, is where Voyager 2 will be. Out there, moving, always. Sleep well tonight, knowing that a small piece of us, a small, cold, silent piece of human civilization, is out there in the galaxy right now, and will be out there for longer than any of us can really imagine. The journey that began on a summer day in 1977 is still happening, every second, every minute, every year. It will still be happening when our species is gone. It will still be happening when our sun is gone. It will still be happening when the Earth is a memory carried only by the golden record attached to Voyager 2's side. Good night. And may the stars, wherever they are drifting tonight, carry our small spacecraft a little farther into the beautiful, empty, endless dark